Okay, I'm going to do some introductory problems having to do with sound, and you should have already watched the video on introduction to some of the mathematics. The mathematics I'll be using in this video would include the relation between the pressure amplitude and the displacement amplitude, and then the intensity expression in terms of placement amplitude and displacement amplitude. I'll probably have to use the fact that the density of air at 20 degrees Celsius is 1.20 kilograms per cubic meter. If you're not told what the temperature is, just assume it's 20 degrees Celsius. That's roughly room temperature. And so that would be the density. And I'll also use the expression for calculating the decibel level. And something that I'll probably have to use in here is, well, certainly we'll need omega equals 2 pi times the frequency at times, and also the speed of sound. And we'll just assume, unless otherwise told, that it's 344 meters per second. If you happen to run across something that says to use 343 meters per second, that's not going to make much difference in whatever answer you get. It's just a slight alteration to the temperature would produce that. So let's go ahead and look at some problems here. First one, sound with spherical wave fronts is emitted from a 1-watt source. So you're going to be having stuff going out in every direction from this 1-watt source. That means the intensity is going to be spread over or the power will be spread over the surface of a sphere. And assuming the energy of the waves is conserved, what is the intensity 1 meter from the source and 2.5 meters from the source? And what is the decibel level in each case? So this is just practice using some of these ideas. Well, we know what the power of the source happens to be. It's 1 watt. And so not very much. We're assuming all of that goes into producing the sound. So something we'll have to keep in mind, the area of a sphere is equal to 4 pi r squared. The intensity of this wave, that's one of the first things we're calculating here, is and this is I of, I'm going to say it's a function of distance, so I of 2.5 meters. It's going to be the power spread over the radius or the area of a sphere, or 1.0 watts over 4 times pi times, whoops, we're starting at 1.0 meters, I forgot. Okay, anyway, 1.0 meters, whoops, 0.0 squared. And that ends up being 8.0 times 10 to the minus 2 watts per square meter. And eventually we have to calculate the decibel level. We may as well do that right now as long as we're on this. So beta at 1.0 is going to equal the 10 dB times the logarithm of I over I naught. Getting the practice or habit of writing that thing. I kind of crowded it here, the blog, but that's the 8.0 times 10 to the minus 2 watts per square meter, and divide by, sometimes it's written as 10 to the minus 12th watts per square meter, but for putting it in your calculator, remember there's a 1 times that. If you don't, you'll come up off by a factor of 10 on the value there, which won't make a huge difference in the decibel level, but Okay, so the beta at 1.0 meters, plug in the stuff there, ends up being 110 decibels, which is actually gotta be pretty loud. So, all right, for part B, we just repeat the calculation at 2.5 meters, and you could probably just do that for yourself, but I naught of, or I of 2.5 meters is going to be, all you do is just stick the 1.0 watts on top. It's still power over 4 pi r squared, so 4 times pi times 2.5 meters squared. And let's see, what are we going to get there? I get 1.3 times 10 to the minus 2 watts per square meter. So just dropped off a bit from that. Okay, and the beta, the decibel level at 2.5 meters. If you calculate that, it's 101 decibels. So drops off a bit. Both of these are in the range where continued exposure to them damage your hearing, although at 101 dB, it would take a long time, but it would eventually happen. So be careful. Okay, this is one that I've kind of done this problem for a long time in various ways. Oh, there's another one. In between, I forgot this one. If the intensity of a sound wave is doubled, what is the change in the dB level? All right, well, this one, we don't have much in the way of numbers in here, except that the intensity is doubled. So let's just suppose that we have some I1, which is some number, and we'll have an I2, which is 2I1. And the decibel levels for each of these things, decibel level for I1, beta 1 would equal 10 dB times the log of I1 over I naught. And beta 2 is going to be 10 dB log of I2 over I naught, but I2 is equal to 2I1. So I'm just going to stick that in here right now, 2I1 over I naught. And we want to know what is beta 2 minus beta 1. How much of a difference? And it turns out as long as the intensity is twice as much, it'll be the same decibel difference every time. So now it'll be this thing minus this thing, but I'm immediately going to start using some properties of logarithms. And the property of the log that I'm going to use is that the log of A over B is equal to log A minus log B, and also that the other property that I'll use is that the log of x times y is equal to log x plus log y. So it's good to keep those things in mind when you're doing stuff like this. Okay, so beta 2, I'm going to write it as, we'll have 10 dB, and then I'll have the log of 2I1 minus log of I naught. And then I'm going to move down a line, minus beta 1, which is, I'll factor out the 10, or put the 10 dB out front, and I'll have the log of I1 minus log of I naught. Okay, since that's a product in there, I'm going to write that as the log of 2 minus or plus the log of I1. So now I've got, I'll call this delta beta. My delta beta is going to equal 10 dB times log of 2 plus log of I1, and then minus log of I naught. So that's my first part. And then I'm going to distribute this minus 10 dB through here, and I'll have minus 10 dB log of I1, and a minus times a minus will be plus 10 dB log I naught. All right, well, let's see. I'll go ahead and write this 10 dB log of 2 plus 10 dB log I1 minus 10 dB log I naught. You're probably foreseeing some of this stuff canceling out. Minus 10 dB log I1 plus 10 dB log I naught. Okay, well, here's minus 10 dB log I naught. Here's plus 10 dB log I naught. Those are gone. 10 dB log I1 minus 10 dB log I1. And all I'm left with is 10 dB log of 2. And so if you plug that into your calculator, you'll find out that the decibel difference is just about 3.0 decibels. So not much of a difference. And this is barely perceptible. Okay. I don't know if you remember the other day that I showed something like that or showed it on a chart. Anyway. Okay. Let's move on to something else. Let's think about dogs here. Tests done on dogs show that they can hear sounds much quieter than humans, sounds which on our dB scale would be between minus 5 dB and minus 15 dBs. So this is a range because different dogs were involved in the tests. So what's the range of sound intensities for these? Okay, well, this is a matter of knowing what the beta level happens to be, minus 5 dB. And actually, I'll kind of split this into two parts here. Okay, and this would be 10 dB times the log of I over I naught. Okay, if we divided both sides here by 10 dB, the dBs go away and I'd have minus 5/10 or minus 0.5 is going to equal log of I over I naught. Use these as exponents on tens on both sides, and you'd get 10 to the minus 0.5 is equal to I over I naught. Multiply both sides by I naught, and I naught times 10 to the minus 0.5 is going to equal the intensity. And on the left side, we'll have 10 to the minus 12th times that 10 to the minus 0.5, 10 to the minus 12th watts per square meter. I should write that out. And that's just a number, but and I get an intensity here of about 3. Yeah, I've only got one sig fig. So about 3 times 10 to the minus 13th watts per square meter. So they can hear a less intense sound, less power per unit area. And if I was to repeat this thing, let's see, I'd have a minus 15 here, and dividing minus 15 dB, dividing by 10 dB, I'd have minus 15 over 10, which is minus 3 halves, and that would be the thing that is in the exponent of the 10 here. So for that other sound, and you could repeat those steps if you want, but I'd have the intensity is going to be 1 times 10 to the minus 12th watts per square meter times 10 to the minus 1.5. And so that's the only thing that changes over here. And that intensity would be, let's see, I get 3 times 10 to the minus 14th. Actually, that makes sense. So a ways down there on the strength scale, a factor of 10 lower, actually. Anyway, kind of interesting. They can hear things you can't hear. I remember one dog we had, I'd be out working in the backyard, and the dog would start barking for seemingly no reason, but uh, a few seconds later, I'd start hearing the UPS truck, and they have a particular sound to their engine. And our dog had been trained, not by me, just by repetition, to start barking whenever it heard the sound of the UPS truck. And if they stopped in front of our house, the dog would bark at the driver coming to deliver the package. And they always went away in response to the dog's barking, it thought. So it was reinforced. Okay. This is a problem. I'm going to try to do 2 ways to show you a couple of different ways that you can do it, but we have a certain loudspeaker produces a sound with a frequency of 2000 hertz. So F is equal to 2000 hertz, something that shows up in the formula that we're going to use, or one of the formulas, I think. Yeah, maybe not. Maybe we don't have to do that. In fact, maybe that's immaterial. Um, oh, yeah, we will need to use that, because at the end, we're going to get the displacement amplitude and the pressure amplitude, actually. But omega is going to be 2 pi times that. So whatever 2000 times that happens to be. Well, calculator says 4000 pi. Anyway, I get about omega is 1 point, let's call this 2.00 times 10 to the third hertz. So we have some significant figures on that thing. Anyway, 1.26 times 10 to the fourth seconds to the minus 1 is what you have for units on there, and I kind of lost that onto another sheet of paper. But we'll go ahead and figure this out. The intensity at 30 meters. Well, we can calculate the knowing the intensity at 6.10 meters, we can figure out the power of the source, and the intensity at any place, 6.10 meters, is going to equal the power of the source divided by 4 pi r squared. And so the power of the source is going to equal, well, let's see, 4 times pi times 6.10 meters squared times 0.960. That's a milliwatt per square meter. I'm going to just stick in a times 10 to the minus third for the milli, and then watts per square meter. And I find out that the power of this source is equal to 0.449 watts. And then it asks, what's the intensity at 30 meters? Okay, so this is all for part A that I'm working on here. Well, the intensity of 30 meters, 30.0 meters, is just going to be that power divided by 4 pi r squared again. Intensity is always like that for a point source, unless we're told otherwise. No reflections, emits in all directions. So I take that power, 0.449 watts, and divide it by 4 times pi times 30.0 meters squared. So it's a matter of just plugging into there, and I get there, I get 3.97 times 10 to the minus fifth watts per square meter. Let me show you another way that I could have done that. And it would be to, let's see, here's a good piece of scrap paper. Without solving for the power of the source on the way through, I could have done this. I could say the intensity at 30.0 meters divided by the intensity at 6.10 meters. And I know this, that's the 0.960 milliwatts per square meter. But this will equal the power of the source divided by 4 times pi times 30.0 meters squared. That's the numerator. And the denominator will be the power of the source divided by 4 times pi times 6.10 meters squared. Okay, well, if you look at the right side here, if I invert this and multiply, things that divide out will be the power of the source and the 4 pi, and all I end up with over here is 6.10 meters squared over 30.0 meters squared. And then the intensity at 30.0 meters equal that at 6.10 meters times this thing, which ends up being 6.10 over 30.0. The units divide out because they're same top and bottom. That thing squared, and you end up with the same number. It's just another way of doing that problem without bothering to calculate the power of the source. So, okay, for part B, what are we supposed to find here? The displacement amplitude at 6.10 meters. We're not doing any of the decibel stuff on this one. Okay, and so for also for part B, we're just going to use one of those equations that I showed you on that shirt or sheet. If it's the displacement amplitude, we're using this formula here. I know I had a bigger print version of that somewhere. Oh, well, I'll copy down the formula. For the displacement amplitude, the intensity is rho v omega squared S sub m squared. So that's what I'll be using here. And the hardest part about this problem is showing what the units end up being, and it's just kind of drives you crazy. But anyway, I'll solve for S sub m squared, and then at the end we'll do take the square of that number, but it's the intensity divided by rho v omega squared. Now, again, this is the density of air. This is the speed of sound. This is omega, which I did figure out. And what we'll have for this is we know what the intensity is at 6.10 meters. It's the 0.960 times 10 to the minus third. That's because it's a milliwatt. Watts per meter squared, and divided by rho, the density of air, 1.20 kilograms per cubic meter. We're assuming we're at 20 degrees Celsius. 344 meters per second. And then omega, up there I've got 1.26 times 10 to the fourth seconds to the minus one, and that is squared. Okay, I'm going to do this on a separate sheet of paper because this is kind of a pain. I'm just going to figure out the units because we've got a horribly complicated mess here. And it's good practice to do this because if you happen to have forgotten a term or something like that, you'll catch it when you analyze the units. So on top, we've got a watt over a meter squared. Well, a watt is a joule per second. So for starters, I'll take joules over seconds. And I also have 1 over meters squared. And that's all what's on the numerator. On the bottom, I have kilograms over meters cubed. I just thought the way I had broken it down to much more primitive units when I first did this, but I thought of a better way to do it. A meter per second, and seconds to the minus one, but they're squared, so that would be 1 over seconds squared. Okay, now a joule you could write as a kilogram meter squared per second squared, but it's also a Newton meter, and I'm going to use that here because I want to end up with newtons on top. So I've got Newton meters over seconds times 1 over meters squared. On the bottom, what have I got? This meter will divide with one of those. So on the bottom here, I'll have kilograms over, where am I? Meters squared. And 1 over seconds cubed. Let's see, did I lose anything? Don't think so. Oh, what am I trying to get? Oh, I want to get S sub m squared. Nope. I was thinking I wanted to get to a pressure. Actually, I do want to break that Newton on top up into kilogram meters per second squared. So I'll just do that. kilogram meters per second squared times meters over second times 1 over meters squared. And on the bottom, I will have kilograms per meter squared and 1 over second cubed. Okay, well, on the bottom or on the top, I'll have meters squared over meters squared. Those will divide out. And I'll have kilograms over seconds cubed. That looks a lot like what I have on the bottom. In fact, I'm going to take this fraction on the bottom, which is kilograms over meters squared second cubed, invert it and multiply. So I'll have meters squared seconds cubed over kilograms, and only thing left is meters squared. So that's good because I'm solving for S sub m squared, the displacement amplitude. So then I just have to plug in the numbers on here. And then we've got the numbers there. What I ended up with for that was, oh, I must have finished this on a second sheet of paper. I did. Okay, anyway, for S sub m squared, actually I solved for S sub m. I ended up getting 1.21 times 10 to the minus 7th meters. That's not very much. Visible light ranges from 4 times 10 to the minus 7th meters to 7 times 10 to the minus 7th meters. So this is a displacement amplitude smaller than the wavelength of the shortest visible light, shortest wavelength visible light. So not very much. Okay, the second half of this was actually even worse in a way. And it is that although I could figure it out from, where did I put those formulas? The relation that the pressure amplitude is V rho omega times M. That would be the easier way to do this than what I did. So pressure amplitude, it's at the same point. So V, speed of sound, 344 meters per second. I don't think we've used this one yet. Rho is the density of air, 1.20 kilograms per cubic meter. And then omega is 1.26 times 10 to the 4th seconds. I'm going to just write it as 1 over seconds and then multiply it by that thing in meters. 1.21 times 10 to the minus 7th meters. So it's just a multiplication problem, except you've got these horrible units. However, I've got 1 over seconds here and 1 over seconds there. That'll give me 1 over seconds squared. I've got meters here, that's meters squared. And actually, I'm going to hang on to one of these. If I keep the kilogram, this meter, which is on top, and the seconds, that'll give me kilogram meters per second squared. That's a Newton. So unit-wise, I'll have a Newton, and I won't have this anymore. I won't have this anymore. And I used up both of those. So now what I've got left is a meter on top and a meter cubed on the bottom. That gives me meters squared on the bottom. And so I've got newtons per meter squared, which is good. That's my units of pressure. And when I calculate this out, I get that the pressure amplitude is equal to 0.630 newtons per square meter. Okay, remember 1 atmosphere is equal to 1.013 times 10 to the 5th newtons per square meter. And so this is 101,000, and this pressure amplitude is only that much. And so not much. It's pretty surprising how small these things can be. And even more surprising is this next problem I'm going to do. We want to calculate the displacement amplitude and pressure amplitude for sound of 1,000 hertz frequency at the threshold of human hearing. Okay, I've already kind of gone through the unit stuff, so I may not spend a lot of time on that on this particular problem. It'll drive you crazy, but you should probably try to convince yourself. All over, I can figure out the intensity right off the bat, though. The 0 dB is the threshold of human hearing, and so that's our beta level, which is 10 dB, which is non-zero, times the log of I over I naught. Okay, well, the left side is 0. The right side must be 0, which means this logarithm has to be 0, and the logarithm, the thing that the logarithm is 0 of is 1. So what we have to have in here is that I is equal to I naught. And you could go through a few steps, but you can also just use the properties of logarithms. If the log of something is 0, that something must be 1. That is the exponent you'd put on a 10 to get 1. 10 to the 0 is equal to 1. Anyway, that means the intensity is 1 times 10 to the minus 12th watts per square meter, and that will equal our formula for the intensity in terms of the displacement amplitude is rho v omega squared s sub m squared. And we already had to go through a whole lot of work to convince ourselves that when we had the metric units on this thing, we ended up with an S sub m that was in meters. And so I'll just say S sub m, I'm going to do 2 algebra steps at once here, is going to be the square root of I over rho v omega squared, which is the square root of 1 times 10 to the minus 12th watts per square meter divided by rho, our good old 1.20 kilograms per cubic meter, times V, 344 meters per second, times omega, which in this case it's 1,000 hertz. 2 times pi times that. 2 pi is 6.28, close enough. Actually, we don't have much in the way of sig figs, but I'll go ahead and plug them in here. But this would actually be, you could call it 6,280 seconds to the minus 1. That's 2 pi times 1,000. And when you work this out, you end up with a value of about 8 times 10 to the minus 12th meters. This is tiny. I don't know, some of you have taken chemistry and may have heard something about the Bohr radius before. When Bohr developed his model of the atom, the he had the electrons being confined to particular orbital distances around the nucleus of the atom. And he was doing this just a handful of years after the discovery of the nucleus, so like less than 5. Anyway, the Bohr radius for the hydrogen atom was 5.3 times 10 to the minus 11th meters, which basically and this would be the diameter of that orbit. If you doubled it, you'd have something that was 10 times as big as this. So this is a tenth the size. It's an amazingly small displacement in the air that's going on in this case. So yikes. And in fact, if it's that small a number, you're going to have to start considering quantum mechanical effects when you really study this stuff. All right. Well, you can do the same thing we did on the other problem, delta P max equaling V rho omega times S max. And same string of stuff, 344 meters per second, 1.20 kilograms per meter cubed. Omega was 6.28 times 10 to the third seconds to the minus 1 again. And then we multiply it by this tiny number. And actually, I would, just for the heck of it, include the sig figs I had on it, but keep only 1 at the end. 4 times 10 to the minus 12th meters. And you end up with a pressure amplitude of 2.03 times 10 to the minus 5th watts per square meter. And this is amazing. Remember, 1 atmosphere, again, is 1.013 times 10 to the 5th. Whoops, what was I doing? This is newtons per square meter. Wow. Anyway, newtons per square meter for 1 atmosphere. Look at that. 2 times 10 to the minus 5th newtons per square meter. So it's the tiniest of fluctuations in the atmospheric pressure, but humans can still hear it, and so can dogs. Dogs can hear stuff down even lower than this. So I should have done something for the dogs, but that's all right. I'll leave that for you if you're interested in it. And finally, what is the pressure amplitude for sound of 1000 hertz frequency at the pain threshold of 125 dB? Well, for 125 dB, let's go ahead and we need to know the intensity for getting the pressure amplitude, because intensity is equal to the pressure amplitude squared divided by rho times V. And it turns out it's independent of the frequency. So we don't need to know that 1000 hertz frequency, which is good. It's only given to 1 sig fig, and this is 3 sig figs. However, we've got beta equaling 10 dB log of I over I naught, and it's 125 dB is what it happens to be. And if I divide that by 10 dB, I get, let's see, log of I over I naught will equal, looks to me like 12.5, and it's dimensionless now. And then I exponentiate both sides, and I'd get I over I. Now I'm solving this. I should have given a whole nother sheet to this. I'm solving this in a way that I don't like you doing your homework at, where you work along a row and then drop down to another row. Better not to do that. Anyway, I over I naught is going to be 10 to the 12.5, or I will equal I naught times 10 to the 12.5. And since I naught is 1 times 10 to the minus 12th, this will end up being 1, well, I'll plug in the numbers here. This is where the units come from. I end up with 10 to the 0.5 watts per square meter. And you can do this on your calculator if you want, but it ends up being, actually, we're down in sig figs. It would be about 3 watts per square meter. Okay, and then we have to figure out the pressure amplitude from that. And delta PM, I'm doing 2 algebra steps at once here to figure out this thing, would equal the square root of I times rho times V, which in this case will be the square root of, oh, let's see, 3 watts per square meter times 1.20 kilograms per meter cubed, and 344 meters per second. And this is hard, figuring out or proving that the units here will end up producing newtons per square meter. But if you work at it long enough, you can figure it out. And you end up with this being about 40 newtons per meter squared. Okay, now that's at the threshold of pain. Okay, 40 parts out of 100,000. Remember, 1 atmosphere is 100,000 or more than 100,000 newtons per square meter. And if a pressure amplitude is 40 of those 100,000s, you end up with pain that's sound that is painfully loud. So that's interesting. Actually, one of the loudest and most dangerous things as far as your hearing is concerned is the end of a vacuum cleaner hose when it's turned on. Because if that gets near your ear, it can cause a pressure difference that's enormous. And don't do that. Keep vacuum cleaner hoses away from your ears. There used to be a YouTube video about this father that was making up his daughter's ponytails. And he took a shop vac, and sucked his daughter's long hair into the thing and then just wrapped a wrappy thing around the ponytail. But it made me so nervous to see that, because you couldn't do that without getting that vacuum cleaner hose close to the person's ears, and you could damage somebody's hearing with that. All right. Well, that's a sampling of a bunch of different problems, or just familiarizing yourself with some of these equations, and try them out on your own. And with some of those unit conversions on here, go ahead and wrestle out some of those and see what you can get.